Hey calculus students, welcome to your summer videos to help you with your summer work packet. I'm going to have 5 total videos on limits. This is the first one. This video is going to do limits and discontinuity. The next video will do limits from piecewise functions. That way you can do it graphically. Then there's going to be 3 videos on doing limits algebraically. There's also going to be videos on logarithms and a video helping you with page 3 of your summer work. So check out as many videos as you need. I would highly recommend watching all 5 of these just to make sure you're all good. Okay, so let's get right to it. This one is just going to be a quick review of limits in general. So the way we talk about limits, the general way we say it is the limit of f of x as x approaches 2 is 12. Now in this case, I'm just plugging in 2 and 12 here just so we have numbers to work with here. The way that you write a limit in math is you're always going to use the letters LIM, and you're going to do the limit of f of x, so your function goes right there. Now you're always going to have what x is approaching underneath the limit. So if x is approaching 2, then I'm just going to put an x with an arrow to 2, and by saying it is 12, is always equal in math, and it equals 12. Whenever you do a limit, what you need to remember is whatever the limit is, whatever it equals, that's the y value. And then obviously whatever x is approaching, that's the x value. The theorem here that you're going to need to know very, very well is that a limit is only going to exist if the limit from the left is equal to the limit from the right. So a limit only exists if the one-sided limits are the same, because the limit from the left and the limit from the right, those are one-sided limits, because you're only coming from one of the sides, the left or the right. So if you want to do it mathematically, not just in words, you would say this: the limit as x approaches a number from the left. This negative here means from the left. Okay, so don't get these confused here. If it equals, here's my little plus sign, the limit as x approaches a from the right, that little plus sign means you're coming from the positive side, then your overall limit right here exists. What am I doing? Okay, anyway. So the overall limit exists right here. Okay, so let's go back to here. What this means, if the limit exists, is that means as you approach x equals 2 from both sides. So if you approach it from the left, let's put a 2 here. Let's say this is my axis. I'm approaching 2 from the left. And if I'm approaching x equals 2 from the right, if I am approaching the same y value from the left and from the right, then the limit's going to exist. And if it approaches 12, then the limit's going to be 12. One thing you have to keep in mind when we do limits is we don't care what actually happens right at 2. Like y doesn't actually have to equal 12, and you'll see pictures of that in the next slide. We only care about what it intends to do at x equals 2. So if it's getting really, really close to 12 as x approaches 2, then the limit is going to be 12, even if it doesn't reach 12. So let me show you some different pictures of that here. Okay, so for our first picture, we just have a regular upside down parabola here. Now in this case, notice that my function actually reaches 12. So if I have my limit from the left, so here's 2, I'm going to approach 2 from the left. So go on your graph, get really, really close to 2 from the left. I'm actually reaching 12, so my limit from the left is 12. As I approach 2 from the right, moving in, moving in, moving in, getting really, really close to 2, my y values are getting infinitely close to 12. They actually reach 12. So therefore, the limit as x approaches 2 is 12, and we're good to go. In this example, notice I have this open circle here. This is, the graph is discontinuous there. We're going to talk about the different types of discontinuity on the next slide. But notice that my graph does not reach 12. But my limit is still 12. In fact, the function's value at 2 doesn't exist. There is nothing going on here. It's not like f of 2 is something else. It just doesn't exist. I don't reach it. However, if I go to, if I approach 2 from the left, so from this side, get on your graph, get closer, closer, closer to 2, my y values are getting really, really close to 12. Approach 2 from the right, so get on your graph, approach 2, closer, 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 closer. I don't reach 12, but I get infinitely close to 12. My graph is intending to go to 12, so my limit is still 12. Because the limit from the left and the limit from the right are the same, my overall limit is 12, so I'm good to go. This graph, you might be thinking it looks really similar to this one, and it does. The only difference is I redefined my function at 2. So once again, just like this one, f of 2 didn't exist here at 12, but I redefined it. So now I would actually say that f of 2 is 6. And you might be thinking, wait a minute, doesn't this fail the vertical line test, so it's not a function? Well, nothing's going on up here. The function's value is 6. However, my limit from the left as x approaches 2 is 12. My limit from the right as x approaches 2 is also 12. So therefore, the overall limit as x approaches 2 is 12 because the one-sided limits are 12, even though the function's value is not 12. So just another quick comment here. My function, once again, does not actually reach 12, but it intends to reach 12. And I redefined my function at 2, and I made it 6. So there are discontinuities going on in my second and third graph. So let's make sure that we know the 3 main types of discontinuities. You're going to need to know these for calculus. First of all, before we talk about discontinuity, let's talk about continuity. A function is continuous on an interval if there are no holes, jumps, gaps, or breaks on the interval. Quick way of saying it is basically it's continuous if you can draw it without lifting up your pencil. So we can have any kind of continuous function, but any type of smooth curve here, I'm not lifting up my pencil to draw it. It's continuous. In calculus, continuous functions are very important because you can only do a derivative of a function if it's continuous, and half of calculus is doing derivatives. So obviously, they're going to be very important for functions to be continuous. 3 main types of discontinuity that you need to know coming into calculus are the following. They're not very hard to remember. If you look at the graph kind of tells you what it is anyway. Let's say I have a rational function here. I know it's rational because I have these asymptotes, my vertical and horizontal asymptote. Notice right here, my vertical asymptote of x equals 2 is breaking my graph in half. And for a vertical asymptote, you can never go through or touch it. Your graph either shoots up or shoots down. If I have a vertical asymptote and it is making my y value shoot up to infinity, or they could shoot down to infinity as well, what we're going to call it is an infinite discontinuity. And that makes sense because my y values are either going to infinity or to a negative infinity. In this case, my limit as x approaches 2 from the left is approaching infinity, and my limit as x approaches 2 from the right is also infinity because I have unbounded y values. They keep going up. However, the overall limit as x approaches 2, don't say it's infinity, even though you might be thinking, well, the left and the right-hand limits are the same, so that means this one should exist. That is the normal rule, but if the overall limit is infinity, that's not an actual number. We're just going to say it doesn't exist and just realize that it's because it goes to infinity. Different calculus books do different things, which is why it's kind of hard to remember this. Usually books will say the one-sided limits are infinity, but the overall limit, they'll say doesn't exist, even if it should be infinity. All right, this one right here, notice the graph approaches, or the y values get close to 10 here. Then the graph jumps up and it continues at y equals 12 and it keeps going up. Well, it's jumping, so this is a jump discontinuity. And here, the limit definitely does not exist either. So my limit does not exist as I approach 2 because the limit as x approaches 2 from the left is 10. And my limit as x approaches 2 from the right, oops, sorry, writing messy. As I approach 2 from the right, my limit is 12. And they're not the same, so the limit doesn't exist. Okay, one more graph here. Here, this one, I have a function that is continuous everywhere except at 2 once again. And this time, I have an open circle at 2, but I'm redefining it up here. So because this graph is continuous everywhere except for one point, we're going to call this a point discontinuity. Some books call this a removable discontinuity. but point is more common. A way to remember it is my graph. If I could just take a single point and put it right there, then it would be continuous. That is not the case here, because even if I was like, oh, if only I could put one point right there and fill in that discontinuity, the graph still wouldn't be continuous because there's a jump. Here, there's nowhere to really even fill in the open circle discontinuity. It's only graphs like this where it looks like it would be completely continuous if you could just put a single point there. That is a point discontinuity. So those are the 3 types of discontinuity you'll need to know for the summer work packet and for next year. In class next year, we'll actually get into the calculus definition of continuity because there's a little more involved. So the next video is going to be limits graphically from piecewise functions.